Hello students. This video is meant to help you do labs in our physics course this semester. Um, so I'm going to work through an example lab. This is not a lab we're doing this semester, it's just an example, but it will hopefully show you what I'm looking for as we do these labs. Alright, so every lab starts with an introduction which has a question that the lab is meant to answer. So for this lab, we want to answer the question, how does the tension in the string supporting a cylinder depend on the depth of that cylinder, the depth that that cylinder is submerged in water? So here we've got this lab, we've got a cylindrical object that's partially submerged in water, and we're measuring the tension in the string, and the deeper the water is underwater, or the deeper the cylinder is underwater, the less tension we will see in the string. We want to both predict what that relationship is going to look like, how does the tension depend on the depth of the cylinder, and then also measure how does that relationship look. And ultimately, the purpose of the lab is to compare our prediction based on physics to our measurements that we do in the lab. Okay, so every lab starts with a question, and this question is really, really important. So then some labs, the physics section, I will go ahead and do all the physics for you, resulting in what's called the physics equation for this lab. This physics equation attempts to answer the question. Sometimes I'll do all the physics for you and just give you the equation. Sometimes I'll tell you what physics to use and expect you to do it to actually arrive at the equation. For this one, for this lab, there are three forces acting on the submerged object. The string is pulling up on the object, the water is pushing up on the object with a buoyant force, and the earth is pulling down on the object with a gravitational force equal to mg. The net force on the object must be zero because the object is not accelerating. That's Newton's first law. So we take what we know, the tension force plus the buoyancy force minus the gravitational force has to equal zero. We rearrange it and we find an equation for the tension force. Now, why did I rearrange it that way? Because we're trying to find how does the tension force depend on the depth. So we want to have an equation for the tension force because we're trying to find how does the tension force depend on stuff. Okay, finally, we're going to take the equation for the volume of a cylinder and plug that in for volume, and we end up with a physics equation for this problem. Now, it's not super important that you understand the physics now, because hopefully we're at the beginning of the semester while you're watching this, but it is going to be important that once we have an equation to use, we know what to do with it. So the first step of every lab is to take this physics equation. This is the equation that comes from Newton's first law and everything we know about tension and gravity and buoyancy, and convert it into what we call a fit equation. And the reason we're going to need a fit equation is that the fit equation is going to be applied to our data to see if it matches our data. So to convert the physics equation here to a fit equation, we do several steps. The first thing I want to do is figure out what are my independent and dependent variables. And this has everything to do with the question that we started with. The dependent variable is the thing that depends on something else. So in this case, the tension in the string is the dependent variable. And we want the dependent variable to be y. So that means the tension in the string, capital T in the equation, should be my y. The independent variable is the thing that the dependent variable depends on. So in this case, the depth that the cylinder is submerged in the water. And in the equation, depth is represented by d. So d is going to be my independent variable. So I'm going to go ahead and start there and rewrite the equation showing what we get when we substitute y for the dependent variable and x for the independent variable. What I'm going to end up with is y equals mg minus rho times pi times r squared times times x times g. And the x is there because this d got turned into an x, and the y is here because this t got turned into a y. Okay, we're almost there. Next, we want to, so first we change the independent variable to x and the dependent variable to y. Next, we want to take the remaining constants and convert them into a and b. Okay, so what do we mean by constants? Constants are things that don't change as the experiment, as we go from one data point in the experiment to the next data point. So what we're going to do with this lab is we're going to lower the cylinder deeper and deeper and deeper and deeper into the water and measure the tension in the string. Well, when we lower the cylinder deeper into the water, the mass of the cylinder does not change, so that's a constant. G, which is related to gravity, also doesn't change, so that's a constant. Rho is the density of the fluid, and that also doesn't change, so that's a constant. Pi is a number, that's a constant. R is the radius of the cylinder, and that doesn't change as we lower it deeper and deeper into the water, so that's a constant. And of course g, again, is a constant, so we have a lot of constants in this equation. However, I cannot just take each constant and call it A, B, C, D, E, F, G like that, because these constants are grouped together. In order to see how they're grouped together, I'm going to rewrite this equation a couple more times actually. So these m and g are multiplied together. So in a sense, they are already sort of one thing, mg. Now these constants are all multiplied by x. So I'm going to sort of take out the x and put it over here at the end. And then rho times pi times r squared times g, all of that stuff is also a constant. So I could say that mg, the first constant in my equation, is equal to a, and rho pi r squared g, the second constant in my equation, is equal to b. Then my resulting equation would be y equals a minus bx. And a good fit equation is going to only have x and y and a and b and maybe c or d or e, or however many a, b's, and c's we need. It could also have a number like 2 in it if you wanted it. If you wanted. Exact numbers are allowed to be part of the equation. So for example, we could actually have pi here, and then pi wouldn't be part of our b. It'd be pi times b times x. Okay, that's probably a little confusing, so let's not worry about that too much. Okay, once I have my fit equation, I want to make sure it actually is the same as the physics equation. So y is t, a is mg, b is rho pi r squared g, and x is d. So if I were to plug back in t for y, mg for a, rho pi r squared g for b, and d for x, I end up with the exact same equation I started with. Okay? So, the result of this part of the lab, the important things that we need to know are, what does the constant A mean? The constant A means mg. What does the constant B mean? The constant B means rho pi r squared g. And what equation should we use to fit the data? Now, you might be a student who can look at this equation and immediately recognize that it's the equation for a straight line. You might not. It's okay. It's a little helpful to be able to recognize that as a straight line. It may be more familiar to you if you said y equals mx plus b. But yeah, that's just the equation for a straight line. All right, let's keep going. So in a real lab, you're going to have a bunch of stuff to measure. In this lab, we would need to measure the radius of the cylinder. We would need to measure the mass of the cylinder. We'd need to find G from the textbook, 9.81. We would need to find the density of water from the textbook, 1,000 kilograms per meter cubed. And we would need to measure the depth of the cylinder at each depth and the tension in the string at each depth. Now, we're not actually doing the lab today because this is just an example, but those were things we would have to measure in class. And what you're going to find from me is that every time we take a measurement, I want to know what the uncertainty is of that measurement. Okay, so this is a good time to go to D2L and look at my reference documents and look at my lab reference documents. And there are a couple of important documents in here. Measurement uncertainty is the one we're going to be thinking about right now. And in fact, just previously, we were talking about converting a physics equation into a fit equation. And if you look at the plotting data reference document, it goes through some examples of how to do that and talks about the steps we would go through to do that. Okay, but right now, we're looking at measurement uncertainty. And so there's a whole document here on how to know what your uncertainty is when you measure something. And I really like this flowchart at the end. I think it's really useful. So let me open up that flowchart a little bit bigger. And I'm not going to go through this whole flowchart in this video, but let's do it at least once. We were trying to measure the radius of the cylinder. So we would do that with a meter stick. And let's say we measured the radius of the cylinder to be 5 millimeters. That would be 0.005 meters. And if we did that with a meter stick, we would go through this flowchart to decide what uncertainty we should use. So, is it possible to make multiple independent measurements? It might be possible. And how would I measure that independently? I would need to get 5 different people to measure that radius, and they would have to not know what the other people had gotten for their answer. Because if I tell you what I got for my answer, you're probably going to get the same answer when you measure it. But if I get 5 different people to measure it, that could be 5 independent measurements. But for whatever reason, maybe we didn't have time to do that. We didn't do it. We only measured it once. So, did we make multiple independent measurements? No, we only measured it once. If you can only measure it once, you must make an informed estimate of your uncertainty. How do you estimate the uncertainty? Will depend on the source of the uncertainty in the measurement. Okay? Some measuring instruments require skill, attention, or reaction time from the human operator. Think of a stopwatch or a set of calipers or a measuring tape. Other instruments will give the same result regardless of who's using them. Think about a digital scale. So, what's the primary source of uncertainty in this particular situation? Now, when we're measuring something with a meter stick, it's the human who has to decide which mark on the meter stick is closest to the thing you're trying to measure. So it's actually the human that is the primary source of uncertainty here. Maybe. Actually, that's something we have to decide when we're doing the measurement. Do you think 5 people would get the exact same answer? Or do you think if 5 people measured it, they might get slightly different answers? If you think if 5 people measured it, they all would get the exact same answer, then actually it's the instrument that is the primary source of uncertainty. If you think if 5 people measured it, they might get slightly different answers, then it's the human that's the source of the uncertainty. So let's assume in this case that when we're measuring the radius of the cylinder, we actually believe that all 5 people would get the exact same answer. So that means it's the instrument itself that determines the uncertainty. Do we have access to a manual? Well, no. There's no manual for a meter stick. So we end up in sort of the worst box on this chart, which is if we think the instrument's the limit, but we don't have access to the manual, then we're going to use half of the smallest digit or marking on the instrument. Meter sticks, the smallest marking is 1 millimeter. So half of the smallest marking would be half of a millimeter. But I need to convert this to meters because we always use meters in physics. So to convert this to meters, I have to divide by 1,000. So 0.0005 meters. Okay, next we measure the mass of the cylinder. And for that, we use a digital scale. So we go through the same thing again. Did we take multiple measurements? No. Is it the human or the instrument? Definitely the instrument, because the digital scale, if I have 5 different people use it, they're all going to get the exact same answer. Do we have access to the manual? Well, in this case, we do. Okay, so our scales in the classroom, the digital scales we use this semester, have an uncertainty that is printed in the manual. It should be given in a form like plus or minus a percentage plus a number. The percent is a percent of the measurement. The number is given in the units of the smallest displayed digit. So, what does that mean? Let's say that when we went to the digital scale, we got this answer from the digital scale. So what's the uncertainty? Well, our digital scale, the uncertainty formula is plus or minus 0.005% plus 2. So how do I do that? I'm going to take 0.005% of this number. Okay? And that's just the number I wrote down from the digital scale. So let's do this. Okay, that calculator is dead. Let me grab a different calculator. All right. So I've got 0.13355 kilograms times 0.005, but 0.005%. So 0.005% is actually 0.005 divided by 100. So I've got to multiply this by 0.00005 to get 0.005%. So I'm going to go ahead and write that down. This number the 0.00005% of 0.13355 gives me, in my calculator, 0.0000668. Okay, and then plus 2. Now, if I literally just do plus 2 kilograms, that would be a huge uncertainty. So it doesn't mean plus 2 kilograms. What it means is plus 2 in the last digit that the instrument was displaying when you took the measurement. So the instrument displayed 0.13355. That 2 means that there's an uncertainty of 2 in that last digit. So this 2 means 0.00002. Because there's no uncertainty in the 1, there's no uncertainty in the 3, there's no uncertainty in this 3, there's no uncertainty in the first 5, but the last 5 has an uncertainty of 2. So the total uncertainty from the scale is the sum of those two numbers. Okay, and so when I add those two numbers together, I get 0.0002668. Okay, so last thing on this chart is how do we report uncertainty? Uncertainties are always an estimate, so it doesn't make sense to write down 4 significant digits when you're doing an estimate. In fact, we're always going to either keep 1 digit or 2 digits when we write down uncertainty. And it's based on a set of rules. We look at the first 3 digits, in this case 266, and we decide which range it's in. So if it's between 100 and 354, which mine is, then I'm going to keep 2 digits. If it's between 355 and 349, then I'll keep 1 digit, and so on. So in this case, I'm only going to keep 2 digits, so 0.27. Okay. Textbook value for G, I will tell you this has an uncertainty of 0.01 meters per second squared. And let's see. Actually, I'm not loving meters. It's better to only write down the units once and to write down the units for the value and the uncertainty together like this. Okay, so 9.81 plus or minus 0.01 meters per second squared, and oops, 1,000. Textbook value for the density of water, 1,000, and we're going to assume that when we looked it up in the textbook, it gave us the uncertainty of that because we don't have any way of knowing that. Same thing for the textbook value for G. For this class, all semester, we're going to use 0.01 for the uncertainty in G. Okay, and so we've got these measurements. Next, we have the actual experiment. The depth of the tube, the depth of the tube, the depth of the tube. So these things were measured with a meter stick, And then the tension on the string, these things were measured with a force probe. So again, uncertainty. I'm really, really focused on uncertainty. How do we know the uncertainty? So we measured the depth with a meter stick. So we go through this chart again. But measuring the depth of this cylinder is a lot harder than measuring its radius. When you measure its radius, it's really easy to set up the meter stick and make sure you're measuring it correctly. But when you're trying to measure how deep this thing is underwater, it's much trickier. And I can imagine if 5 different people measured it and didn't know the answers that the other people gave, they might get different answers. And that's just because of how measuring with a meter stick works, right? You've got this meter stick with a bunch of lines on it, and you've got to decide which line is closest to the thing you're trying to measure. And different people might give different answers. And in this case, I'm saying that if one person picked 3 millimeters, another person could pick either 2 millimeters or maybe even 1 millimeter or 4 millimeters or 5 millimeters. They could be different by as many as plus or minus 2 millimeters. Now that's an educated guess. That's an estimate. You have to make an educated guess for how far off would people be if several different people tried to measure this. It's basically like, how sure are you that you're picking the right millimeter line when you're doing this measurement? So it's going to be a little bit subjective. But in this case, I think the uncertainty might be about 2 millimeters. You're going to gain more and more experience throughout the semester with measurement uncertainty and trying to estimate how uncertain those measurements are. Okay, finally, for the tension in the string, we did 5 independent measurements. We measured it 5 different times, and we got 5 different values. So, back to my chart. Is it possible to make multiple independent measurements? Yes. Okay, take at least 5 independent measurements. Use the average of your trials as your measurement. Use the standard error as your uncertainty. Okay, great. So we are going to do that. We are going to go to a standard error calculator. And if you just Google standard error calculator, the very first link is Good Calculators, and it works fine. And we're going to take these values. We're going to copy it into the calculator. Now this calculator wants commas between our values, so I've got to put in the commas. And then I hit calculate, and it will tell me the average, 1.27006, and it will tell me the standard error, 0.00549. Okay, but remember, 54987. Remember though, we don't write down 5 digits for uncertainties. This is the correct standard error, but standard error is an estimate of our uncertainty. So we don't need 5 digits, we only need 2 digits. So, and actually, I think this is in the range where we only need 1 digit, 0.005. So this is saying that there's no uncertainty, right? There's no uncertainty in the 1. There's no uncertainty in this 2. There is no uncertainty in this 7. And there's an uncertainty of plus or minus 5 in that 0. So this 0 could actually be 5 lower or 5 higher, which means these next 2 digits don't really matter at all. So when you know your uncertainty, the number of digits that you keep in your value should match the number of digits that we have in our uncertainty. For example, there's 1, 2, 3 digits here, so there should be 1, 2, 3 digits here. Okay, let's do another one. go ahead and put this in. Getting my commas between my values. Okay, and calculate. And this one had an average of 1.2589 and an uncertainty of 0.019199. Okay, and this is in the range where we keep 2 digits. So this is 0.019. And again, this means that there's an uncertainty of 0 in this 1. There's an uncertainty of 0 in this 2. There's an uncertainty of 1 in this 5. And an uncertainty of 9 in this 8. Okay, so the digits that have uncertainty, I need to make sure I keep. So, but the digits beyond that, I don't need. So I'm going to round this to 1.259 so that the number of digits in the uncertainty, 1, 2, 3, equals the number of digits in the value that I kept, 1, 1, 2, 3. Not the number of significant digits, but the number of actual digits. Right? This 0 refers to this 2, this 1 refers to this 5, and this 9 refers to this 9, so we had to keep all those digits. Okay, and then we would continue to do that for the rest of these values. Okay, now, I've been explaining in words, but your job would be now to explain in writing how you took your measurements and how you determined the uncertainty for each measurement. So for everything I measured, okay, so 1, for the radius of the cylinder, we measured the radius with a meter stick. We only took one measurement. We believed that if 5 people measured the radius, they would all get the exact same answer. So the only uncertainty is from the meter stick itself. In this case, half of 1 millimeter. Okay. For the mass of the cylinder, we measured the mass with a digital scale. We only took one measurement. We believe if 5 people measured, the only uncertainty is, okay, we believe if 5 people measured the mass, they would all get the exact same answer, so the only uncertainty was from the digital scale itself. In this case, 0.005% plus 2. So the uncertainty was 0.13355 kilograms times 0.00005 plus 0.00002. Okay, this is the kilograms. This part is that part, and this part is this part, equals 0.00027 kilograms. Okay, so when you actually have to do a calculation for your uncertainty, great to go ahead and show me the calculation. All right, 3 for the depth of the cylinder, we used a meter stick. We only took one measurement. We believed that if 5 people measured the depth, they might differ from each other by as much as 2 millimeters or 0.002 meters. Okay, and for the tension, we used a digital tension scale. We measured 5 times and used the average as the measurement and the standard error as the uncertainty. Calculations were done using good calculator, standard error. Okay, and so look, what we've done here is we've very carefully explained how we measured each thing we measured and how we determined the uncertainty of each thing we measured. In this lab, we had to measure 4 different things: the radius of the cylinder, the mass of the cylinder, the depth of the cylinder, and the tension in the string. So I need 4 answers to this question. How did you measure it? How did you determine the uncertainty? Okay, now we get into the analysis section, which is where we make our graphs. So for this, we are going to use the website called PhysicsPlot. And to make our graph, we are going to first download an example CSV file. So we'll call that data.csv. And then we're going to open that file. So on my computer, that went into the downloads folder, and here is data.csv. And this is only an example. It is not exactly what we're using. But it shows us the format we want. The first thing is the label for the x-axis. So this is going to be depth in meters. And the second thing is the label for the y-axis. So this is going to be tension in newtons. The first column here are the depth values. So this is going to be 0.030, 0.060, 0.090, 0.12, 0.15, and 0.18. And since I don't have a last column, I'll delete that one. I've only got 6 data points. My uncertainties are 0.002, 0.002, 0.002, 0.002, 0.002, 0.002. And my tensions, these are my values. Hold on. I think I've got some values from when I did this lab once before. Since I didn't plug them all into the thing there. Buoyancy. Okay, cool. Here are some values. Whoops. Okay. Those might not be the same. Those aren't the same values from here, but for you they would be. They would be your values. Okay. So I've got my tension values and I've got my uncertainty values. And right, we would only keep the correct number of digits. Yes. Okay. So let's pretend that's my data. So I'm going to save that data file. Um, and again, this would be your real data from your real collection. Okay. Um, so now we'll browse for that data file. Under my downloads, it's data. I don't know why it doesn't want me to pick that one. Um, downloads, data. Okay. Browse file. Downloads. Okay. Maybe it was because it was open. Once I closed Excel, it was okay. All right, so I can just now double check to make sure this is my data. Oh God, did I actually close? Okay, there it is. Um, okay, graph your data with physics plot. Include your results on a separate page. You should include the main graph, the residual graph, the chi-squared, fit equation, and fit parameters. All right, so how do we do that? We're going to use physics plot. Okay, so we loaded the data. This is our correct data. It's got the correct values of x, the correct values of x uncertainty, the correct values of y, the correct values of y uncertainty, and here's a graph of just the data. Okay, and then it says we want to enter the equation. So what equation? Well, we're going to enter the equation that we have up here, except we're not going to include the y equals. So here's some examples of what that might look like. So for us, this is going to be a minus b times x. And look, you have to put in a star, that's a shift 8, anytime you want to multiply two things. If you just do bx, it's not going to work. But b times x, that works. And then a title, example graph. You won't say example graph. Maybe you'll use the title of the lab for your plot title. Okay, set equation. And it starts out with a graph where the line is nowhere near our actual line, but that's okay. We can perform an auto fit. And now we have a graph where the line is the best possible line through our data. And let me bring this over here so we can get a better look at it. So here's our graph of our data points with the uncertainties shown, our line, which is our equation that we think is supposed to fit the data, and then our residuals, where it shows how far away each data point is from the line. Okay, and then down here, we've got all of our statistics. So what we're going to do is we are going to copy all this and put it into our lab report. So I'm just going to screen copy this. And paste it into my lab report. So we've done this. We've made our graph. It includes the main graph, the residual, and then down here is all of the chi-squared and fit parameters and stuff. And up here is the fit equation. Okay, was the curve a good fit? All right, so here is where, again, you are going to have to go to the reference documents. If you go to your reference documents, interpreting the curve fit, part one, does the curve fit the data? You've got some criteria here for answering that, and you've got some language for how you might explain your answer. There's some very specific criteria. Does the curve have the same shape as the data? Are the data points close enough to the curve? These are the two criteria. Now the curve here is the orange line, and the data points are these blue crosses. Do they have the same shape? Well, it's kind of hard to tell, and the best way to tell for sure is to look at the residuals. And what we're looking for is a pattern. If this has a steady downhill pattern, a steady uphill pattern, a steady frown, upside down parabola, a steady smile, right side up parabola, then we would call that a pattern, and we would say that the data has a different shape than the curve, or the curve has a different shape from the data. But if none of those patterns exist, then they have the same shape. And in this case, none of those patterns exist, so we say the residuals are random, and that is an indication of a good fit. So I'm going to start off by saying the residuals are random. Okay, so that is a so the curve has the same shape as the data. Okay, next we're going to look at the chi-squared. And that is going to tell us if the points are close enough or not. So chi-squared is a mathematical, statistical calculation. We'll talk about it a little bit more in class, but here is the chi-squared for this data set, and I guess we will maybe look at the reduced chi-squared. So the reduced chi-squared is supposed to be close to 1. And in this case, the reduced chi-squared is like 3.6, plus or minus 0.7. So that is very far away from 1. The reduced chi-squared is much larger than 1, 3.6 plus or minus 0.7. So the data points are not close enough to the curve. Okay, so 2 criteria that we're looking for. Does the curve have the same shape as the data? And are the data points close enough to the curve? The curve does have the same shape because the residuals are random, but the data points are not close enough because the reduced chi-squared is too big. We could also look at the chi-squared. Notice this says times 1,000. So our chi-squared is actually 14.6 plus or minus 2.8. So our chi-squared here is 14.6 plus or minus 2.8. So if we look at this, that chi-squared is supposed to equal the number of degrees of freedom, which in this problem there are 4 degrees of freedom. So the chi-squared is supposed to be equal to 4, and it's equal to 14.6. It's too big. So, are the residuals appropriate? In this case, the answer is no. The residuals are too big. So if the residuals are too big, but the residuals are random, then we end up in this box. Okay? So, the residuals are random, but the chi-squared is too big. So the data points are not close enough to the curve. Therefore, the curve is not a good fit for the data. Okay. Was the curve a good fit for your data? No. This is our conclusion to the first question. Was the curve a good fit for your data? Justify our answer? This is how we justified our answer. Here's what a lot of students forget to do. What does this mean about the assumptions that were made when generating the physics model? Well, if we're in this box, the curve does not fit the data, but there is evidence that the physics may be appropriate for explaining the data. Why? Because if the actual physics equation was wrong, then we would see a pattern in the residuals. So the fact that there's no pattern in the residuals tells us that the assumptions in the physics models might be okay. For this experiment. Okay, the assumptions for the physics model might be okay for this experiment because the residuals were random. Okay, determine the value of the acceleration due to gravity from the values of A or B in your fit. And the known values of the density of water and the radius of the cylinder include uncertainty in your calculation. Whew, this video is getting really long. It's okay. So how do we do this? Notice it says, determine the experimental value for the acceleration due to gravity from the values of A or B. This is like really, really important. It means that we are going to start with A and B to get our answers. So I know that B is equal to rho pi r squared g. So I'm actually going to copy this down and bring it down here. So I'm going to say I know that B equals that. And this is important because the graph told me what B is. We know what B is. B is 0.6658. Since I know what big B is, and I also know what rho, pi, r, and g and r are, I can use this to find g. In fact, this is going to tell me, by doing a little bit of algebra, that g should equal whatever value we got for b divided by rho times pi times r squared. So g should equal the value we got for b, 0.6658, divided by rho, which is 1,000, times pi, which is 3.14159, times r squared, which was 0.005 squared. Let's make sure that's right. The radius of the cylinder was 0.005. Yeah. Okay, so I can plug all that in. And 0.6658 divided by 1,000 times 3.14159 times 0.005 squared, close parentheses, equals 8.477 meters per second squared. Isn't G supposed to be 9.81? And we're getting 8.477? that seems like way off. Um, but in order to really know if it's way off, we have to know what the uncertainty in this value is. So, how do we find uncertainty? Well, we go back to our reference documents on D2L. And we go to uncertainty in calculations. And you've got my document on uncertainty in calculations, which I think is wonderful and well written and can explain everything. And they've also got one that was prepared by a student, which I think is wonderful and well written and very helpful. So let's look at the student's notes. Calculations with uncertainty, we have two rules, one for addition and subtraction and one for multiplication and division. Well, is this addition and subtraction or multiplication and division? Pretty obviously multiplication and division. So we're going to use the multiplication and division rule. So in the multiplication and division rule, if you have numbers multiplied together, the uncertainty in the answer divided by the answer is going to be the uncertainty in the numbers that you multiplied together divided by their values. So insert an equation. So the uncertainty in G, and that sigma is pronounced uncertainty in divided by G, should be equal to all the things that we're multiplying and dividing. So in this case, the uncertainty in B over B plus the uncertainty in rho over rho plus the uncertainty in pi, over pi plus the uncertainty in r over r. But look, the r is squared. And r squared is really the same thing as r times r. Does that make sense? So there's two of them. So if it's like r times r, then I'm going to need two of these. And another way of writing two of these is just to put a 2 in front of it. Like that. So the uncertainty in G over G plus the uncertainty in B over B plus the uncertainty in rho over rho plus the uncertainty in pi over pi plus 2 times the uncertainty in R over R is equal to the uncertainty in G over G. But we don't really want the uncertainty in G over G. We just want the uncertainty in G. So let's rewrite this equation. And on this side, we just want the uncertainty in G. So we're going to multiply both sides of this equation by G. Okay. Whew, we are almost done. Hopefully you'll watch this in 2x or skip to the parts you need to be reminded of. So the uncertainty in G is the uncertainty in B over B. All right, we get this from physics plot. Physics plot tells us that the uncertainty in B was 0.505, and B was equal to 0.6658. The uncertainty in rho we get from the textbook. It was 2, so 2 over 1,000. The uncertainty in pi, well, pi doesn't have any uncertainty. It's an exact number. So 0 over pi plus 2 times the uncertainty in r. Okay, I remember that was 0.0005, half of a millimeter, divided by r, 0.005, 5 millimeters, times g, 8.477. We're going to use the value that we calculated. So this is going to tell me the uncertainty in G. Whew. Okay, so 0.505 divided by 0.6658 plus 2 over 1,000 plus, I'm going to skip that one because 0 over 3.14159 is 0, plus 2 times 0.005 divided by, 0005 divided by 0.005, close parentheses, times 8.477 equals, I typed that in wrong. Wow. I really typed that in wrong. Okay, let me try again. 0.505 divided by 0.6658 plus 2 over 1,000 plus 0 over pi plus 2 times 0.0005 divided by 0.005, close parentheses, times 8.477 equals. What's going on here? 0.505 divided by 0.6658 plus 2 over 1,000 plus 0.00 divided by 0.005, close parentheses, equals. That is not right. Ah! You know, I typed in the same thing 4 times, and I typed in what I had written down. The problem is, what I had written down was wrong. It's 0.0505. Okay, there we go. Times 8.477. Alright, so I get, after typing it wrong in my calculator 5 times, I think I got the right answer, 2.355. Alright, so now we need to actually write this with the correct formatting. So G equals 8.477 plus or minus 2.355 meters per second squared. And this is almost perfect, but we need significant digits. And remember that uncertainties always either have only 1 or 2 significant digits. And this is in the range where it would need 2 significant digits, 2.3. So this 2 means there's a plus or minus of 2 in that 8. This 3 means there's a plus or minus 3 in that 4. And we didn't keep any extra digits beyond this 3, so we don't need to keep any extra digits beyond that 4. So this is going to be 8.5 plus or minus 2.3. That's my final answer for determine the experimental value of the acceleration due to gravity. The last thing we need to know is the textbook value for the experimental acceleration due to gravity is 9.8 plus or minus 0.01. Compare your value to the textbook value, and do they agree? Use a t-score to justify your answer. So again, back to our reference documents. Comparing with uncertainty, here we've got a document that describes how we calculate the t-score and how we interpret the t-score. So to calculate a t-score, we say the t-score is equal to the absolute value. Remember, that means if you get a negative, you drop it. The absolute value of 8.5 minus 9.81. That is the value that I got minus the expected value, divided by the uncertainty in the value that I got plus the uncertainty in the expected value. Okay, so that's equal to 8.5 minus 9.81 is negative 1.31, but we dropped the negative. So 1.31 divided by 2.31 equals 0.57. So that t-score is less than 1. So what do we say about whether they agree when the t-score is less than 1? The two values are not measurably different from each other, or the two values are within statistical uncertainty, or the two values are in agreement, or the difference between the two values is likely due to chance. So I'm going to say the measured value of G from the experiment is not measurably different from the textbook value. And one thing I'm going to do before I turn it in is change the color of my answers to be different from the color of the questions to make it easier for the grader to read my answers. So anything that's my answer should be a different color. Well, black's okay. Just not the purple, because, oops, did I just delete my answers? Undo. Huh? I don't know what's happening. Okay, there we go. Okay. Fair. All right. Let's see. So these are all answers. So they should be in a different color. Probably do it as you're writing the document. Make sure your answers are in a different color than my questions. Or, you know, highlighted or something. Okay, and this is ready to turn in. Look, there's a lot to this. If this seems overwhelming, that's totally understandable. If this is right at the beginning of the semester, we're going to be talking about each of these parts as we go through the semester, but we're going to be doing these exact same steps in every lab, and by the time you get to the end of the semester, you should be really, really good at it. So hopefully that'll be the case, and I will see you guys later.